So this is going to be like a journey to discover OpenSearch AI superpowers. First things, I work in a company based in Paris called Adelean. We are expert in search technologies. Our domain of expertise gravitate around Elasticsearch, OpenSearch, and Solr. And we are provider of consulting and training. And we develop HU, which is an e-commerce enterprise search solution, and all.site, which is a collaborative search engine. So as I said, as it has been such a well, long journey, I would say. So 3 years since the beta release, 13 May 2021. And since then, many features have been developed, features that gravitate around artificial intelligence. Some features like neural semantic search and neural sparse search related to semantic and so vector search. Some other more recent and more related to the possibility of connecting large language models like connectors, LLM guardrails, and then we have also space for improvements because with vector search we really need a lot of improvements because it's really a powerful technology, but we need resources, and when we scale, it's quite complicated to put in place. And so we have also space for improvement. And so we are at the version 2.17. Probably 17.1 or 70.2. Last time I checked was 70.1. So we're gonna start with hope so. Wait. No, I'm not sure. Okay, I'm gonna share the window. Okay. So yes, nice, this one. So we're gonna check all the superpowers or part of them. So starting from semantic search. So this is really a simplification of semantic search. So imagine you have a zoo and you want to transform each animal in a zoo into a numerical form. So you take different features of your animals. For example, in this case, I took size, friendliness, and intelligence, and you give a score from 0 to 1 to indicate, for example, that a cat, it's quite small, so it has a score of 0 to 25. It's quite friendly. Who doesn't think a cat is friendly? No, I'm not thinking. And quite smart. So we can try to represent our zoo with numbers. And that's exactly what we are doing with the dense semantic search. We are taking our documents, we are using a model of machine learning, and we are transforming our documents or part of our documents into vectors, into numerical representation. And why we are doing this? Because we can put our document into a vectorial space, just as we can do with a zoo. So we have a dog, which is super close to a cat, into our vectorial space. We have an elephant, which is more on the left side. And the distance indicates really the similarity between the two elements of our vector space. So, for example, a duck is going to be more similar to a cat based on the characteristic we indicated, so size, friendliness, and intelligence. Now, once again, this is a simplification. Now you have to imagine that a vector model is going to create 100 or even 1,000 of dimensions. So it's impossible, it's extremely hard to represent 100 or 1,000 dimensions. And each dimension of our vector is going to represent somehow some feature of our document. And each feature is going to represent the document semantically. Why semantically? Because essentially when we are looking for, probably I have, no, I don't have it. When we are looking for our documents, normally with lexical search, we check for keywords. So we want an exact match of keyword, or almost an exact match of keyword with our query. But when we're using semantic search, we can work on semantics. So we don't have to have a 100% match, as we may have with lexical search. So I wanted to show you how we can implement semantic search in OpenSearch right now. You can all see it. So we have two phases. We have a first phase where we have our ingest pipeline, so indexation part on our left. With the ingest pipeline, we have two processors. The first processor is a text chunking processor. Essentially, we want to cut our document in different chunks. We want to do this because models are limited. They can't get in input more than a certain amount of token. If we give a bigger document to a model that doesn't allow more than a certain amount of document, the model is not gonna create the vector on this on the second part of the document. So it's gonna exclude from the semantic representation the second part of the document. That's why we do text chunking. So we're cutting the document in different parts. And then we have text embedding. So we are creating our vector. And on the other side, so we have the search part. We use a search pipeline with a neural query. And we're using a neural query enricher, which can seem extremely hard, something extremely esoteric. But it just, we want to associate our model to our field of our documents to a model. So we don't have to specify it each time we do our query. So extremely useful. And then we do perform our search. So to show you how this works, yeah, we have okay. So I have already registered my model here. When we register your model in OpenSearch, you're gonna be able to use it through a model ID. The model ID is, in this case, is this one. It's extremely easy to use. So, for example, here we have the phrase "Hello OpenSearch," and we can transform this phrase into a vector, which is gonna be a vector of 768 dimension. So it's not a 3-dimension vector; it's 768. It's way, let's say, bigger. And each of this element is gonna represent a characteristic of our document. In this case, of my phrase "Hello OpenSearch." So I want to start from a simple index. In this index, we have some movies from the past, like 1901 and so on. We have some plot. So we have the summary of our film. And what we're gonna do here is we're gonna create our first pipeline. So as I said, in the first pipeline, we use a text chunking processor. We are cutting our document in different chunks. So each document is gonna be 512 token, which is the limit for this for the model I'm gonna use. We have an overlap rate, so each window is gonna overlap of 20% here. And we also specify our tokenizer. And then we just have a field map. We want to associate our input field, so as I said, plot, to our output field, so passed chunk. So we're going to take our plot, we're going to cut it, we're going to put it on a new field called passed chunk. And then we have the second processor. So first processor, second processor, easy text embedding. So we have our model, and we take our passed chunk, and we transform it to a vector. So I'm going to do it. I'm going to create this pipeline. Then at search time, this one is extremely easy. It's as I said, it's an neural query enricher. So we said for the field plot embedding, we're going to use the model here. Model ID is, once again, always the same. We always use the same model for indexation and search part. Let's create the search pipeline. I'm going to delete this index because I already did this at home. So I'm going to create a new index here. I'm going to use the default pipeline, the one I created here for ingestion, and the search pipeline, the one I've created here for the search part. And then what is important here is also the type here is the type K9 vector. As you may notice, it's inside a nested object because, as I said, we are creating a chunk, a vector for each chunk. And so we're gonna we have a type of K9 vector with 368 dimension and that type float. And I'm gonna reindex from my movie source to my new index, and there we have our chunks. There we have just one chunk because the document was short and then 512 token. And then we have our vector that looks exactly like this. And for other documents, we have also bigger plot. So we have more chunks. So in this case, we have multiple chunks. I think 2 chunks. Yeah, we have 2 chunks. So we have common here. And then we can do vector search. So in this case, we are just we're not using the model ID because we are using a neural query enricher. Normally, here we will put model ID equal to our model ID, but we don't have to do it because we did it before. So we can search for the sound of silence. Retrieve only 2 documents here. Once again, we are querying on the nested object. And we looked for the sound of silence, and this is magic because this is magic of the vector search. In the text, there is nothing that talks about, I mean, there is no word that match sound of silence, literally, but it's a movie about a family who moves to the suburbs hoping for a quiet life. So the sound of silence and a quiet life. Who knows the movie? It's Surba Night. I don't know. It's a movie of the 1904. So quite old. So yes, this one was dense vector search. Why we call it dense vector search? Because each element of our vector is a number and is never 0. It's all the elements are represented. And then we have another technique, sparse vectors. Sparse vectors are, let's say, less powerful somehow, less precise, but they are way easier to implement, and they are less heavy than dense vectors. In this case, we are operating some sort of term expansion. So we have, for example, we have a text here. Orangutans are native to the rainforest of Indonesia, and we can use a model to associate some more words to this text. For example, the model can generate some sort of synonyms to rainforest, so to enrich our document with more context. How this is actually working? Because we give this to a model, and then we got some sort of tokens here with some weight. And okay, so I'm going to explain you how this is working. So first thing, this is this is the first part of our model of sparse vector. So the first thing is tokenization. So it's going to take the phrase, it's going to cut it in different tokens. Then it's going to use transformer and attention mechanism. It's going to enrich each of this token with the context. Because if you take orange out of its context, can be orange the fruit, can be orange the city, can be orange the company. The transformer and attention mechanism can enrich the words, each token here, with really its context. Then we pass it to a masked language modeling add. In this case, we are masking each token one by one. In this case, the token masked was rainforest. And then the masked language modeling add is going to try to guess which word goes at the place of the mask. So it's going to create tokens. It's going to create tokens like rainforest, wildlife, because orangutans are native to the wildlife of Indonesia, goes quite well on it. And it's going to create some probability for each token. And then this probability is going to be aggregated into an importance estimation that gives us the different tokens with their importance related to the phrase we gave to the model. So once we saw how sparse model works, we can work with OpenSearch and search for sparse vectors. Once again, it's quite straightforward. It's quite easy to implement. Always the same. In this pipeline, we have a specific processor to do this. It's called sparse encoding processor. We use our model. We transform our document to a sparse vector, and then we sparse vector are stocked into feature field. Is less heavy than dense vectors because we can implement it into the inverted index. It's easier to implement. And on the search side, we still have the neural query enricher. Once again, it's optional. And then we also have the neural sparse shoe face processor, which we can use to speed the search time. So to show you how this is working, once again, I already implemented the model. I already deployed the model. So the model here just is an ID. It's a sparse model. It's the OpenSearch Neural Sparse Encoding V2. And once again, the ingest pipeline is quite straightforward. We're just gonna map our input field to the output field. I'm gonna delete this. I'm gonna create a new index. Into this new index, we have the new type plot parse type rank features, which is exactly Lucene type, and we can do our reindex normally, and we can look at our beautiful sparse vector. So we have tokens that are like extracted with the process we saw before, with their importance into the phrase, and we have many of them. And then we can create a search pipeline. Once again, it's quite straightforward. We just here, this is just a parameter to indicate how many token has to be used in the first and in the second phase of this search pipeline of this neural sparse two-phase processor. And once again, the neural query enricher. And we can use our search pipeline normally we find a movie that has some Indian inside. And yeah, we have some Indian that is that has some sort of concept related to the sound of silence, and that has concept related to the world is on fire, like burning arrow set the Indian camp on fire. I guess this is the way. This is the right. And yeah, I can't see anything about the sound of silence, but this is mainly related to the fact that we gave more weight to some search rather than to others. So we saw how conversational hybrid search work, and let's move forward to connectors. So and conversational search. So as I said, you can deploy your own compatible model in your cluster, but not all models are compatible. Some way to bypass this problem is to use connectors to connect external model hosted externally to your cluster. There are some blueprint. You can find them on OpenSearch documentation for the most common, for example, large language models, or for vector models. So there are blueprints that you can reuse. They are quite straightforward, quite easy to understand. And if you want to connect a locally deployed LLM, we had a talk at the OpenSearch Europe conference. So I will give you the slide later if you want to see the talk and the other amazing talk at the conference in Berlin. And so why do we want to connect an LLM to a model? Because we want to do retrieval-augmented generation. So the LLM are extremely powerful. We want to, in this case, in the case of retrieval-augmented generation, we want to get our document from our OpenSearch index. We want to add an instruction prompt and pass the document and the prompt to the LLM in order to have an answer that is different. That is we'll see during the demo. We can do many things with the LLM. The LLM have the capacity of understanding the context, the document, and our instruction. And once again, I'm gonna switch to the demo. Not many demo. And so I already, once again, created my connector. Of course, I had to hide my OpenAI key. And once again, the connector or the model is just an ID. So there you have. We have a context field list that is the part of the document we want to pass to the LLM. We have a system prompt, which is the classical system prompt of any large language model, and then we have some user instruction. You can have fun with it, which is essentially some sort of prompt. So the idea is that we have two phases here. We are gonna reuse our RAG pipeline. So I'm gonna create it once again. And we're gonna we have two phases. So we're gonna retrieve our documents. Like I wrote, what is an example of a fish movie, for example? Use the model ID of the dense vector search in this case. So this is kind of the same query I used before. Pass only 3 documents to the LLM, and hopefully the LLM is going to answer, because it's going to connect to OpenAI service. And I asked to the LLM to create me a summary of the 3 documents. So we have a document which is the Surban, I don't know how to pronounce this, Surbanite, I guess. One movie about whatever it is. Okay, the martyred president. Sorry for the pronunciation. And then we have all American movies. Some other movie is going to be like some Teddy thing, I guess. And so the LLM got answer us. So this is a way to enrich our documents or our answer at query time with some sort of summary of our movies. So it's going to talk about the Surbanite in case you want to see it tonight, or the martyred president. Okay, horrible movies, probably they're good movies, but I'm not going to watch them tonight. And then they were introduced recently. It's agent and tools. So we were at the .ai recently, and every single talk was about agent and tools, because agent and tools allow the LLM to communicate with the environment. So the LLM, wherever it doesn't know about something, is going to try to use its tools, the tools we provide them. Provided, I don't know if I should say it or him for an LLM. And then it's gonna get the result back from the tool, and it's gonna create a proper answer. This is exactly what happens with GPT when we ask what is the weather today. Has anyone done that? Oh, okay, I'm not the only one. Only for them. No one does that. Okay. And so you can here ChatGPT is going to retrieve the information from the internet, because of course it doesn't know, and it's going to give us a proper answer. And in OpenSearch you have many tools. I think in the future there's going to be so many more tools. And for example, we can combine different tools to create our own agent. So, for example, we can use a PPL tool to create and execute a query on a given index, given instruction, and then we can also call the cat indexes to get the name of the index, which is, if in case we don't have the name of the index, we can associate, we can put together different tools in order to create our own agent. Then I'm gonna go super fast on this. OpenSearch has introduced recently the question answering. So question answering model, that kind of model that we called with Elasticsearch, we could deploy internally to our cluster. We didn't have full compatibility. It's quite a cool feature to use. Essentially, you can, given a context, extract the answer from the context given a context and a question. It's quite easy and straightforward to deploy, but there are many other use cases that are not available yet into OpenSearch and that are available on the dark side of the moon on Elasticsearch. And like classification, zero classification, name entity recognition. But once again, there's a super cool workaround. I tested it and it works just wonderful. And it's just deploy the model externally or internally, and then you use connectors. Well, essentially, we can use connectors to do it. So like for example, here I used I created a connector connected to a named entity recognition model. I extract entity given a document, a field of our document. Of course, I'm gonna use the same field as before, the plot field. And I put this into an ingest pipeline with a machine learning inference processor. So it's not the last demo. There's another one. So I had some demo about question answering. So yeah, one really important thing is to use your own connector. You have to add the URL into a regist form into the cluster setting. So in this case, I'm going to use some Hugging Face API inference model. So I'm going to connect directly to the Hugging Face API inference. Hopefully, it's going to work. And then you can just register your model. Once again, it's quite straightforward. You put your endpoint, you use your model as a parameter, then you got your Hugging Face key that I'm going to delete just after the demo. And really easy, you send a post to this URL, and you get and you send this payload. You can do whatever you want. It's really easy to configure. And then you got a model ID. Once again, I already done this, so I'm not going to do it again. That you can use to test with the predict API. So in this case, I sent a phrase: Pietro is Italian, lives in Paris, and the model of this case is a BERT base. Is gonna give me an answer with the different entities. So we have Pietro is a person, Italian is miscellaneous, and Paris is a place. Once again, easy. We can just implement ML inference processor into a new pipeline to do this at indexation time. So every time we're gonna index something into our index, we're gonna use this processor to extract the different entity. And I'm gonna jump this to show you how this is working. So for example, okay, we have here our plot, and the different entities has been generated. Irish is miscellaneous, Carrie Nation is a person, and we have nation as a person. I already did this, and I said myself, oh, nation is not a person, but I mean actually it's the name of someone. So nation's face. So the model is always right. So trust your machine learning model. And last technology that we can use with OpenSearch, it's Reranking. So we want to rank our document in case we have some ranking problems, some relevance problem. we have two techniques. We have the learning to rank using a judgment list, and then we have the possibility to use a machine learning model. Can be a cross-encoder supported, and or a B-encoded model. Think is not supported. And once again, it's the same idea. We are using a search pipeline in this case because we retrieve our documents, like we search for 10 documents, and then we use the ranker to re-rank, to reorder the documents. So the machine learning model is gonna use its intelligence to reorder the different document, is gonna re-rank them. And last demo, it's quite cool. So once again, I already deployed my model here, still from again phase. I created it, deployed it, and I'm using it into a re-ranking processor, into a new pipeline. So if I search for time traveling into my index with the lexical, so keyword search, I found a movie about sleeping car to Trieste. Okay, which is a thriller, but I feel like it doesn't talk about time traveling. Why this? Because the document is the plot is quite long, so it contains, I think, 100 of tokens, 100 of words, and so when you search for a long document, you have a lot of noise. So in this case, if we look for time, is just in time, and if you look for traveling, is a train traveling in the opposite direction. So the document is not at all talking about time traveling. If you use a re-ranker, so we are using the search pipeline here, and our re-ranker on the same field, it's quite incredible. It's going to take some time. It's quite incredible how the re-ranker works, because already the title will speak for itself. We found a movie about adventures in time. Beagles. That's Beagles the dog. I don't know. I didn't check this. Okay. I don't know. I'll check later. Okay. I hope it was not too much. I hope it was not too fast. And if you have any question, well, I'm here to answer you, or later. It depends by if we have enough time.
Des questions? Ouais. Oui. Faut juste tenir ça.
Moi, je sais pas.
So sometimes in with your first demo, you were showing that we can make embeddings, and then we can search on, like, we can chunk the documents, and then we can search our query against those chunking. But sometimes, like in some companies, we have documents where we don't have plain English kind of documents. We have some technical documents. They have a lot of model numbers, these kind of things. And sometimes we got a requirement of searching against those model numbers, those kind of things. So, like, do you suggest me some methods to tackle that kind of problems where we don't have English as a as our language? I mean, like, because it's a technical document, so English doesn't make a big difference.
I mean, personally, I'm a fan of hybrid search. So as soon you have, we're never gonna implement a search engine made only by semantic search. To be fair, I mean, I think semantic search is something more that can give you some proper answer in a certain context. Like you can find the diamond into your collection of data. But for the rest, I still think the lexical, so keyword search is the way. So just use hybrid search, and yeah, then the model is true that we saw this at where I work. We have a lot of French documents, and most of the model are like they speak more English, like. And so even if we have some French model, their precision is not going to be as good as the English ones. So yeah, for other language that are not English, it's a bit harder. But I think, yeah, hybrid search is the way.
All right, thank you.
Welcome.
Other questions? Maybe a quick question on chunking. So you showed that you have to chunk the input text by yourself because it's not done automatically by OpenSearch. No.
Well,
So you can do it. You can implement a pipeline, but
yeah, I mean, part if they did something recently, yeah, it's the only way to do it right now. But it's still quite straightforward, I think, because at the end you just implement your pipeline, and I mean, chunking goes with the model. So the model, you know that the model is going to accept a certain amount of token. So you just set a pipeline for every field you want to chunk at the amount of token.
So if you change the model, you just have to think of changing the pipeline also. Great.
Yeah.